Are you preparing for your AI/ML engineer, data scientist, or AI research interviews, or being asked to explain core AI concepts like neural networks, activation functions, or how deep learning models actually work? If yes, then this video is a must watch. One of the key things interviewers look for is your ability to explain and apply deep learning fundamentals, something that comes up in nearly every AI/ML interviews. Without a strong foundation, you could struggle with questions on model accuracy, overfitting, or choosing the right architecture for your real-world problem. In this video, our expert will break down the fundamentals of deep learning, covering perceptrons, activation functions, neural network layers, and how these come together to power applications like image recognition and natural language processing. This is the same approach that many of our learners, such as Debashish, Arun, and Roshan, followed to transition into high-paying AI/ML roles by mastering these real-world skills. And if you want to fast-track your journey, make sure to join our free masterclass on AI/ML, GenAI, data science, and Agentic AI. You can register through the link given in the description below. Also, this video is taken from our cloud certification and job focus program. So let's take a look.
Today we are going to start the deep learning part. Okay. So what is deep learning? So the deep learning is nothing but the subset, or you can say the subfield of the machine learning, where we are going to use artificial neural networks in order to solve the complex problem. Okay. And these neural networks are created by taking the inspiration how the human brain process the information. Okay. And it is like forming a very complex neural network, and where so many, you can say, the mathematical calculations happens. Okay. And based on the mathematical calculations we got some result. Okay. So neural network can be used for the regression task as well as for the classification task. Okay. So how to use this regression and classification problems, uh, and how we can use deep learning neural networks, we'll see in this section. Okay. Now this deep learning is the combination of the neural networks. Okay. So this kind of neural networks we form there, where we are having some input layer, hidden layer, and the output layer. Okay. So this type of, you can say, the neural network we are going to use. Okay. The application uh, of this deep learning, or you can say the neural network, is very vast. Okay. So nowadays everywhere, in most of the algorithm, this neural network is being used. Okay. Now, be it like the image and video recognition, speech recognition, predictive analysis, fraud detection, natural language processing, supply chain optimization, recommendation system, medical diagnosis, okay, chatbot, natural language processing, time series analysis, everywhere we are using this neural network. Now, in order to like create the neural network, we are having some frameworks available in Python. Okay. Now, in the machine learning, we have used some libraries like scikit-learn, pandas, numpy, matplotlib. Okay. And that libraries were performing some specific task. Okay. Like it is used for the EDA, right? Data pre-processing and training purpose. So similar kind of task we can be performed for the neural networks. Okay. So very famous neural network frameworks are TensorFlow and the PyTorch. Okay. So what is TensorFlow? It is an open source deep learning framework developed by Google Brain team, and it was released back in 2015. Okay. Now it is most widely used framework. Okay. TensorFlow is most widely used framework because it supports it is having strong support for the production. Okay. Now you can use it on like on your local machine as well as on some a cloud kind of platform. Okay, so TensorFlow is having that large support. Now when we talk about some you can say platforms of the machines, okay, where we can use some CPUs, GPUs or TPUs, so we can use this TensorFlow on any kind of machine, and it supports different platforms like central processing unit, CPUs, graphical processing unit, and tensor processing unit. Okay, now this tensor processing unit is developed by Google only, and it is like proprietary uh, uh, machines that is available only at the Google cloud. Okay, and most of the Google products are integrated with these TPU machines. Okay, now in support with this TensorFlow, Keras API is mostly used. Okay, because this TensorFlow is providing some uh, normal Pythonic kind of structure, but in order to use in very sophisticated way, Keras is helping us. Okay, so Keras is a high level API that is used along with this TensorFlow. Okay, now similar to this TensorFlow, we are having the PyTorch framework. So it is also open source deep learning framework, and it was developed by Facebook's AI Research Lab. Okay, and it was released in 2016. Okay, now it is more similar to the Pythonic uh, kind of a coding. Okay, and it is very developer friendly, but it is most widely used in research and the academia. Okay, if you are doing some research and if you want to write down some algorithm from the scratch, in that case PyTorch is very helpful because it is giving you the flexibility for the debugging. Okay, it is like more supportive, and it is having dynamic graph type of structure. Okay, so it is not static in nature, it is very dynamic in nature, but it is mostly used for you can say the research purpose. Okay, now if you are if you want to create some production ready applications, so for that the TensorFlow framework is most widely used. Now we'll see what kind of you can say the neural networks that are formed. Okay, and how the neural network work behind the scene. Okay, so we'll understand first the single layer perceptron model. Okay, single layer perceptron model. So what happens in case of the single layer perceptron model? We are having a structure which is very similar to the neuron structure which is available in our body. Okay, so here on the right hand side you can see that this is the neuron. Okay, and this neuron is having several parts. Okay, like here the dendrites are there. Okay, then the axon terminals are there. So on the dendrites we will be getting some input. Okay, so this input will be in the form of light or the touch or the taste, right? So we are having so many sensory organs, and a human can feel the sense of touch, sense of light, right? So these are the inputs. Okay, so these inputs are getting transferred to the human brain, right? So there is a neural network is present. Okay, the or you can say the network of all the neurons is there, and in our brain we process that information whatever maybe we are going to receive, and after processing our body organ behaves like this. Okay, so the brain sends some activation for different organs, and according to that activation uh, our body organ behaves, right? So either like if it is sending that okay, please hold some object, or please release some object, or wave your hands, okay, blink your eyes, yell, or scream out loud, like cry, or be happy, or okay. So there are so many, you can say, the actions that human takes based on some input, okay. So this processing happens with the help of this neuron structure, okay. The nervous system plays very important role there. And it's similar kind of, you can say, the network has been created by the engineers, okay. So if you see here, this is a single, you can say, the neuron, okay. And based on that, a single layer perceptron was created, okay. So here we will be having some inputs, okay, like x1, x2, x3, x4, okay. So this one will be x2, x3 and x4, okay. So x1, x2, x3 and x4. And there is, we are having some nucleus kind of structure, okay. So this nucleus kind of structure is called as neuron. This is called as neuron, okay. Now in that neuron, some mathematical calculations happen, and based on this calculation we will be getting some output, okay. So this is very similar to this, you can say, the neuron, okay, which is available here, okay. And here we are having only one, you can say, the neuron. And this neuron like of structure is called as perceptron there, okay. This is called as perceptron, okay, perceptron. Now what happens in this perceptron, we'll see here, okay. Now suppose if we are having a data like this, okay, where we are having some input features, okay, we are having some input features like this, okay. So here we are having one independent feature x1, then x2, then x3, then x4, okay. Now based on these features, we are having some target, right, the dependent variable. And this dependent variable contains only two classes, okay. So either there will be zero class or the one class is there, okay. So we are having multiple, you can say, the features, and one column, target column, and in that we will be having two classes only. So this is the problem of, you can say, the binary classification, okay, binary classification, okay. Now this binary classification problem is solved by this single layer perceptron when these classes are uh, like separated by the linear boundary, okay. So suppose if we plot this kind of structure there, okay. And if we are having the classes uh, available like this, okay. And if it is very easy to draw some decision boundary, okay, like this single line there, okay. So if it is very easily, you can say, linearly separable kind of thing, so for that case this single layer perceptron is used, okay. So what happens in case of single layer perceptron, we are having input layer and the output layer there, okay. We are having some input layer and the output layer, okay. So how this input layer and the output layer work? So here what we do, we create some neural network like this, okay. Like here we are having this input layer. So this x1, x2, x3 and x4 all are the inputs. So these inputs are nothing but these features, okay, x1, x2, x3 and x4. And at the end we are having this output. So output is nothing but the class 0 or 1 class, okay. Now there is one, you can say, the neuron, and at this neuron we are having some calculations done, okay. Like it is very similar to the equation of, you can say, the linear regression, okay. So we know uh, the linear regression equation. Okay, so this is y hat equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. Okay, now here there are 1 2 3 and 4 features. Okay, therefore this equation will look like this, right? Now this is a normal linear regression equation. Now when we use this equation in case of, you can say, the neural network, so this equation is modified as this. Okay, w0 plus w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. Okay, only this beta term will become w, because in a neural network these w's are called as weights. Okay, these are called as weights. These are called as weights. Okay, now this is the term which is called as bias. Okay, which is called as bias. So instead of this w there, it is modified like this: b, okay, b0 you can say, then w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. Okay, so this kind of equation it is formed. And when we summarize this equation, okay, so this will look like this. Okay, so summation of wi xi, I varies from 1 to n plus b. Okay, plus b. So this is the equation which is used for the prediction. Okay, for the prediction task here. Okay, now here if you see that if you are having n equal to 4, so this equation will be roll out like this. Okay, like this: w1 x1 w2 x2 w3 x3 plus w4 x4, and in that we are adding this bias term. Okay, so now in case of linear regression, these are called as coefficients. These are called as coefficients, or sometimes it is called as slope parameters, right? Slope parameters. Okay, and this term is called as intercept there. Intercept. Okay, intercept. But in case of this neural network, the same parameters and the intercept are called as weights and the biases. Okay, so whatever maybe we are multiplying with the feature values, okay, those coefficients are called as weights there, and this is called as bias. Okay, now the task of our neural network is to find out the values of these weights and the biases. Okay, the task of the neural network is to find out the values of the weights and the biases. Okay, so there is ultimate aim of that particular neural network. Okay, now how these weights and biases are used there? So here you can see that if we are having this kind of, you can say, the neural network where in the input layer we are having the number of neurons which is similar to the number of, you can say, the features that is available in our data set. Okay, now here we are having four inputs: 1 2 3 and 4. Okay, and it is connected with some output neuron there. Okay, so here if you see that at each connection there we are having these weight terms. Okay, so this is w1 w2 w3 and the w4 term is there, right? So these are the weight terms, and we, what we do, we multiply this x1 with w1, x2 with w2, x3 with w3 and x4 with w4, so that we will be getting this equation. Okay, this equation up to this part. Okay, w1 x1 w2 x2 w3 x3 w4 x4 part. And after that, add after doing this multiplication and addition, we will be adding some bias term there. Okay, we will be adding some bias term there. Okay, now after calculation, okay, after doing this calculation, we will be getting some value. Okay, now this value will be continuous in nature. Okay, here the nature of the output will be continuous. the nature of the output will be continuous. Okay. Now suppose if we are solving some linear regression problem where the target column is continuous in nature, so we will be getting these values, okay, continuous values, that will be our output. Okay, so this continuous output will be our predicted value. Okay, y value will be this. Okay, but here when we are having this kind of, you can say, the classification problem, okay, where we are having this kind of classification problem, then that time what we need to do, we need to fit this continuous value into some function, and that function here is called as activation function. That function here, it is called as activation function. And the you can say the use of this activation function is to add a non-linearity, into our output. Okay, into our output. Okay, so the task of this activation function is to add non-linearity into our output, okay, of this neuron. Okay, now in perceptron model we are having this step function there. Okay, step function. So the output of the step function is either 0 or 1. Okay, there are only two outputs, either 0 or the 1. Okay, now if the values over here, okay, whatever we are getting after the calculation, okay, if these values are negative in nature, that is if these values are less than 0, then we will be having 0 class there. Okay, and if the values are positive or equal to 0, then we will be having one value there. Okay, so there is only two values, either 0 or the 1 value. Okay, now based on the values of this calculation inside this neuron, okay, when we fit that output into the step function, okay, so we will be getting either 0 or the 1. Okay, now here we can easily give the value names, like the class name here, like it is a 0 and this one is the 1 class. Okay, now suppose if the values are greater than 0 or equal to 0, then we can straightforward say that we are having class 1. And if the values are negative in nature, then we can directly say that the predicted class is 0 class. Okay, whatever may be. Okay, whether it is male, female, accepted, rejected, okay, approved, not approved, these kind of classes will be there. Okay, we will be labeling them as a 0 or 1. So it will be either predicting the values like it is 0 or the 1. Okay, now here in case of this single layer perceptron, we are having only, you can say, the input layer and the output layer. Okay, and it is only used for the linearly separable, you can say, the data. Okay, so where the data is very simple in nature and we can easily draw some linear boundary there. Okay, so based on that we can use this single layer perceptron. But in a real life scenario we don't have that simple data. Okay, so if we are having some data which is very complex in nature, okay, which is very complex in nature, so for that we will be using this multi-layer perceptron. Okay, for that we are using this multi-layer perceptron. Now in case of this multi-layer perceptron, what happens, we add hidden layer there. Okay, along with the input layer and the output layer, we introduce hidden layer there. Okay, so if there is only single layer present, hidden layer present, then that kind of multi-layer perceptron is the single layer perceptron. And if you want to add multiple layers there, okay, so multiple layer perceptron is there. Okay, so we are having freedom to add the number of hidden layers there. Okay, number of hidden layers there. Okay, now here as well we will be having similar kind of structure. Okay, similar kind of structure. Okay, say similar to this single layer perceptron, but instead of giving the direct output here, what it will do, it will like create some complex neural network there. Okay, and it is trying to solve some complex, you can say, the equations there. Okay, now here if you see that suppose if we are having some data where we are having only three, you can say, the inputs. Okay, so x1, okay, x2 and the x3. Suppose this kind of you can say input is there. Okay, and in the hidden layer we have introduced three neurons. Okay, in the hidden layer we have introduced three neurons. Okay, now suppose if our data will look like this. Okay, suppose our data will look like this, where we are having two classes. Okay, where we are having some two classes. Okay, now here we cannot, you can say, separate these. Okay, by you can say the single line, right? So if we try to separate it out with the single line. Okay, with the single line, so what will happen there? It will either separate this like this, or it can separate like this, or it can separate like this. Okay, so if we draw only a single line there. Okay, so either one of the single decision boundary can be used. Okay, now here we can easily say that this is not easily linearly separable kind of you can say the data. Okay, so in that case what we do, we normally use this multi-layer perceptron. Okay, we use multi-layer perceptron. And how this multi-layer perceptron work? So we introduce hidden layer in between the input and the output layer. Okay, input and the output layer. Now when we try to do this connection like this. Okay, x1 along with some hidden layer. So what it will do, it will initiate with some you can say the weights there. Okay, so for here if we consider the combination of this x1 along with this or you can say only this h, this is the hidden layer first neuron. Okay, so what it will do here, so it will initialize the weights like this. Okay, so suppose this is the w1 which is used for this x1 and the h1. Then there is a w2, okay, which is used for this x2 and the h1. And there is w3 there. Okay, w3 there, which is used for the x3 and the h1 combination there. Okay, now the same calculation will be performed there. Okay, same calculation will be performed there, which is like x1 w1 x1 plus w2 x2 plus w3 x3. Okay, and again we will be adding some bias here. Okay, so suppose this is the bias 1, so here we will be adding some bias term. Okay, so this combination here, it is like linear in nature. Okay, now after that what we will do, we will be fitting this output, okay, of this calculation into you can say some activation function there in order to add some non-linearity. Okay, so here this term if I say that this is the z1 term. Okay, so suppose there I'm using this activation function. Okay, so this is the sigmoid activation function. So this activation function I am using there. So what I will do, I will just fit that into this activation function. So output of that you can say the operation will be the a1. Okay, so we will be getting the output of these you can say after fitting into this activation function is the a1, is the a1 there. Okay, now here it is the binary classification problem and we need to get some output here. Okay, as well. So after getting this output here as well, we will be having some you can say the weights. Okay, so suppose this is the wo1. So this is the output layer where we will be combining all those you can say the neurons from the hidden layer to the neuron in the output layer. Okay, so for this combination as well, we will be having some you can say the weights there. Okay, suppose these weights will be like wo1, wo2 and wo3. Okay, now here as well the same calculation will be happening. Okay, here the same calculation will happen. Now this calculation here, if you see, it is it a similar kind of calculation will happen for this h2 and h3 as well. Okay, so this is the neuron number 2 and this one is the neuron number 3. Okay, so suppose if there is a combination between this h1 x1 and h2 is weight number you can say 4. Okay, then between this x2 and h2 it is w5, and x3 and the h2 it is w6 there. Okay, now the same kind of z2 value is calculated there, and after fitting into that activation function we will be getting a2 there. How this will happen? So here we will be having this kind of structure. Okay, w4 x1 plus w5 x2 plus w6 x3. Okay, plus here the bias term will be added like b2. Okay, so the b2 term will be added and there we will be getting z2. Now after fitting that z into this activation function we will be getting a2 there. Okay, similarly for this third neuron we will be getting z3 value, and when we put that z3 inside the activation function we will be getting a3. Okay, so these values will be calculated at this you can say the neuron. Okay, now after that the same calculation will happen for the output there. Okay, for the output there. Okay, for the output there. So what kind of calculation will happen there? So this will be like a1, which will be multiplied by wo1 plus wo2 a2 plus wo3 a3, and add this level one you can say the bias term will be added. Suppose this is the bo term. Okay, so bo term will be added and we will be getting the value of z there. Okay, so this is the zo. Suppose now here as well we will be fitting that zo into some activation function. Okay, so there we will be getting a output, and that a output will be the predicted output. Okay, now we will be doing this comparison. Okay, of the predicted output along with this actual output. So y is the actual value there, y is the actual value there, and here y hat is the predicted value. Okay, predicted value. Now when we do the comparison or take the difference between them, okay, so y minus y hat, so we will be getting some loss there, we will be getting some loss there. Okay, and our target is to reduce this loss. Okay, our target is to reduce this loss. So what happens here when we are having this kind of you can say the non-linear structure? So here you can see this one neuron will be giving us a single line. Okay, this one neuron will be giving us the single line, and this second neuron will give us the second single line, and this third neuron will give us the third single line. Okay, so suppose this line that we have got there from the a1. Okay, then there may be the chances that this is the line we got for this a2, and this is the line where we will be getting for this a3. Okay, so these kind of three lines will be drawn there. Okay, and at the output what it will do, it will perform some smoothing. Okay, it will perform some smoothing so that this complex structure or complex decision boundary will be you can say the drawn. Okay, so that this complex decision boundary will be drawn, and whenever we are having the classification problem which are non-linear in nature, which are non-linear in nature, so for that this will help. Okay, by drawing the multiple lines, and after drawing the multiple lines we will be trying to you can say the smooth out all those decision boundaries so that it will look like a very good a finer you can say the decision boundary there. Okay, so this kind of you can say the operation is some input layer. Okay, so in this input layer we are having some neurons. Okay, we are having some neurons. Okay, in the hidden layer as well, in the hidden layer as well So we are having some neuron there as well. Okay, suppose here I am having two neurons. Okay, in the input layer, suppose if I am having three neurons, and here I am having two neurons, and in the output layer, we are having neurons as well. Okay, we are having some neurons as well. Okay, now there we try to form some neural network. Okay, like this. So suppose this is our you can say the input. Okay, so this is the x1, this one is the x2, and this one is the x3. Okay, now what it will do, it will try to make combination like this. Okay, so with this neuron, this is the combination which is made like this. Okay, now with this second neuron, the combination will be like this. Okay, now when we combine all those you can say the neurons there, okay, we will be getting some random initialization of the weights. Okay, so here we will be getting w1, w2, and w3. Okay, and in the second case, here we will be getting the weight value like w4, w5, and the w6 there. Okay, now after getting these values, some bias term will be added there. Okay, some bias term will be added there. So for this one neuron, we are having one bias term, and second neuron we are having second bias term. Okay, now up to here, the combination of the input and the hidden layer is created. Okay, so all the combinations has been created there. Now after that, there is like a time to create the neural network between this output and the hidden layer. Okay, so there as well we will be having this kind of you can say the neural network combination. Okay, so here we are having some another weights initialized. Okay, so suppose I am just giving name here wo1. So since it is connected between the output layer and the hidden layer there, so o is for the output. Okay, so wait for the output layer. Okay, so wait output 1 and wait output 2. So wo1 and wo2 I'm giving there. So after that, again here one you can say the bias will be added for this neuron there. Okay, so this is I'm considering this is bo. Okay, so b for o for output, and after that we will be getting the output there. Okay, now these weights and the biases are the trainable parameters, are the trainable parameters trainable parameters. Okay, and our neural network is trying to find out the optimum value of these weights and the biases. Okay, now these weights and the biases are having effect like this. Okay, so here if you see that this is forming the equation of the line only. Okay, so when we multiply this w with x1, w2 with x2, है ना? Whenever we are having this multiplication and addition, so this is trying to find out like the equation of the line. Okay, so here for this neuron 1, we will be having one equation of the line, and for this second you can say the neuron, we will be having second equation of the line. Okay, now here the equation of the line will look like this: w1 x1 plus w2 x2, w2 x2. Okay, and then w3 x3, sorry, w2 x2 and w3 x3 plus here bias term will be added, and that will be giving us the continuous value. Now if you look at this equation, so we know that are the these are the slope values. Okay, these are the slope values, and this is the intercept value. Now here it is these slope values are also called as weights there. Okay, these are called as weights here, and this intercept is called as bias there. Okay, bias. Now these weights are used, or it the you can say the significance of these weights is to give the importance. Okay, give the importance to the feature, to these features. Okay, to these features. So based on the value of these weights, we the algorithm learns how important these features are in order to get the output. Okay, in order to get the output. Okay, and bias is the intercept term. So whenever we are having the zero, you can say the values of these weights, so because of this intercept we will be having some value. Okay, so it will be like used to avoid a dead neuron problem. Okay, it is used to avoid some dead neuron problem, so that we some values will be passed to the next layer. Okay, so if all the values will become zero and the bias value will also be zero, then no information will be passed from the input to the output layer there. Okay, so this is the importance of these weights and the biases. Okay, so these weights and biases will decide what will be the output that we will be getting here. Okay, we will be getting here. Okay, now in case of this multi-layer perceptron, what happens, this single neuron will try to form these single lines there. Okay, single lines there. Now here we are solving like the classification problem, right? So for the classification problem we need to add some non-linearity into our you can say the data. Okay, so in order to add the non-linearity we are having activation function here. We are having activation function. Okay, activation function. So what we do, we fit this output. Okay, linear output, this is the linear output, and add some non-linearity, like suppose this is a sigma activation function, and in that we will be fitting that linear values, so that we will be getting non-linear values. Okay, so this a1 is the non-linear value, so this is the non-linearity that will be added into our data. Okay, so when we add multiple, you can say the number of neurons there, so multiple lines will be added which will be used to separate or create some non-linear decision boundaries like this. Okay, non-linear decision boundaries like this. Okay, now suppose if you are having more complex data there, if you are having more complex data, so in that case what we do, we will be adding more number of hidden layers. Okay, there we will be adding some more number of hidden layers. Okay, so this is the playground there. Okay, so here if you see that we are having a very simple problem like this. Okay, where we are doing this binary classification task. Okay, so here we will be adding no hidden layer. Okay, so when we don't have any hidden layer, okay, so this kind of you can say the problem is called as single layer perceptron problem, right? Single layer perceptron problem. So when we fit into our you can say the neural network like this, so suppose if we are having only two features. Okay, so this x1 and the x2, so when I hover my mouse upon it, so there you can see it is try to create this vertical line, and this one is try to create this horizontal line. Okay, so this is trying to create some you can say the decision boundary there. Okay, now this is the very simple you can say the classification problem. So when I start this learning there, okay, so there you can see in 77 epochs only I'll be getting this beautiful decision boundary, where these two classes are you can say easily distinguished. Okay, from each other, and we can easily say that this is the zero or this is the one class, right? So this is very simple you can say the problem, where we don't even required any hidden layer. Okay, we don't, here you can see we are having only zero hidden layer. So this kind of you can say the algorithm is called as single layer perceptron. But what if we are having this kind of you can say the complex structure of the data, where we cannot distinguish between all those classes with a single you can say the line. Okay, so when we do this kind of you can say, or we when we try to uh, draw some line there. Okay, so there you can see either it can misclassify like this, or it can misclassify like this, right? So there never be like a two class classification will happen. Okay, so for that what we need to do, we need to add some complexity into our neural network. Okay, so for that we add one hidden layer, suppose. Okay, so here I am adding one hidden layer. Okay, so here it is calculating some values, okay, and trying to, you can say, the classify this, okay. So suppose initially I am having just two neurons in this hidden layer, and if I try to, you can say, like draw this or train my model, okay. So there you can see, because of these two neurons, I am getting these two lines there, okay. So this is the line number one, and this one is the line number two. So which is like the decision boundary, okay, which is the decision boundary. Now if I add one more neuron there, okay, so here if you see, if I just add one more neuron, so it will try to like uh, draw some particular line, okay, in such a way that it will be adding some more complexity, okay, in my model. So here you can see, here the complex decision line is like a created, okay. So here from this visual you can easily identify that can be created with the help of two lines, right. And here this is the straight line still there, okay. Now if I try to add some more neurons like this, okay, some more neurons, and when I execute this, okay, so here you can see, as I increases the number of neurons into my neural network, so it is like trying to draw some beautiful decision boundaries, and create some like the classification, okay, very easily, okay. So because of this, what happens, I'm trying to add the complexity, okay. So because of this number of neurons, the flexibility to add the non-linearity is increases, okay. Now if you want to like perform the same task on this only, okay, so suppose this is the another, you can say, the problem where more, you can say, the complex data is present. Now again for the same, if I just plot this, so here you can see the beautiful you can say the decision boundary is added, okay. Now as we increase the complexity, okay, so here you can see this is one of the most complex, you can say, the classification problem, okay. Now if again, if I just start this learning, okay, so here you can see, as compared to the previous two problems where the data is somewhat simpler than this current data, so it is taking more time to classify all those, you can say, the problems. And here if you see that there is, I say, the difference between the training and the test loss, it is changing very like very slow there, okay. Now after some epochs, okay, it is taking like a 1700 epochs now, so it is trying to draw some decision boundary, right. So for more complex data, it's taking more time. Now what if I want to like do or solve this problem in less time? So for that, what I will do, I will increase hidden layers, okay, and also uh, I'm adding some more number of neurons there, okay. Suppose here if I'm having three number of hidden layers, okay, and now if I try to like classify, okay, so here you can see the classification has started, okay, and it is trying to solve this problem, okay, and the very complex neural network has been formed there. Now the test loss and the training loss is not changing, okay, even the epochs are more in nature, okay. So here the values are not changing much, so I can say that the convergence point has reached, and it is not a uh, sufficient, okay. So I need to tune this activation function there, okay. So I will be adding more non-linearity into my data. So there you can see. Now previously we have used this sigmoid activation function, okay. Now I'm using this ReLU activation function, so we can compare the result of these two activation function, okay. So here in this problem the ReLU activation function is working somewhat well, okay. So if I just don't use this regularization, and if I just change the learning rate there, okay, Now if I just try to like classify this, okay, after changing these parameters, so we'll see whether it is working well or not. Okay, it will try to classify now here on this visual only. We can easily understand that okay, this is trying to form some decision boundary, right? So this orange color here, if you see that it is only for these orange points up to here. Okay, now it is not working well for this, it is doing some small misclassification, and after that it is also classifying this orange is matches with this orange dots, right? So easily understand. Okay, so it is trying to create some, you can say, the classification there. Okay, now neural network. Okay, so in order to get these trainable parameters, okay, suppose here in this neural network, if I just tell you that now I'm telling you that how to decide how many neurons should be present in input layer, in the hidden layer, and in the output layer. Okay, so the number of neurons that are present in the input layer are equal to the number of features present in our data. Okay, so number of neurons equal to number of features. Okay, in case of this input layer. Okay, so whatever maybe our data is. Okay, so here you can see if we are having this kind of data where 1 2 3 and 4 features are there. Okay, so for this we will be having this 1 2 3 and 4 number of neurons in the input layer. Okay, so a number of neurons in the input layer equal to the number of features. Okay, number of features. Now how many number of neurons to be present in this hidden layer? So there is no, you can say, such a rule that you will be having this much of neurons in the hidden layer. Okay, so that is up to you. That is up to you, and that you will be decide by comparing the multiple times. Okay, by training the model multiple times with some different values of this number of neurons in the hidden layer. Okay, so here, but the right you can say the thumb rule is say that you need to use 2 to the power n rule. Okay, so here either you can use the 8 number of neurons, 16 neurons, 32, then 64, 128, 256, 512, 1024, and so on and so forth. Okay, so this will be the 2 to the power n, right? So 2 to the power n means what? So if we take 2 cube, so this is 8. If we just take 2 to the power 4, so this will be 16 there. Okay, similarly for this. Okay, so the thumb rule say that you can use this combination, but if you want to use like 10 number of neurons or 15 number of neurons, okay, then you can use it. But the researcher says that whenever you are using this kind of combination, okay, 8 16 32 64 256 there, so it is giving you the good results. So if you are having some more number of features there, okay, so suppose if there are so many features there, so the value of the neurons in the hidden layer like 128, 256, and 512 are giving the good results. Okay, as compared to other combinations. If the number of future features are less here, so either you can use this 8 or 16, and according to the number of features that are present in our data set, we can select the range for this hidden layer. Okay, now because of these hidden layers, what happens, there is the combination of these trainable parameters, the numbers of that trainable parameters got increase or decrease. So I will tell you how this will happen. Okay, now how many trainable parameters will be available for the single, you can say, the training. Okay, now here in the output layer, in the output layer, the number of neurons are present. Okay, so if it is regression or binary classification problem, binary classification problem, then in output there will be one neuron. There will be one neuron. Okay. If this is a multi-class classification problem, okay, so the number of neurons at the output layer will be equal to number of classes. Okay. So if it is a linear regression problem or the binary classification problem, there will be only one neuron in the output layer. If it is a multi-class classification problem, suppose there are 5 classes that are present in the target column. So the number of neuron in the output layer will be equal to 5. Okay. So the number of neuron present in the output layer will be equal to the number of classes present in the target column in case of multi-class classification. Okay. So here we are having this binary classification problem, suppose. So for that purpose, we will be using only one neuron there. We will be using only one neuron there. Okay. Now, if suppose it is a multi-class classification problem. So suppose if we are having 3 classes, suppose if we are having 3 classes, okay, in the target column, okay, like yes, no, maybe. Okay, so there are 3 classes, yes, no, maybe. So how this neural network will be formed? Like here in the input layer, we are having the number of neurons equal to the number of features. Here we are having the power of 2 combination, and in the output layer, since there are 3 classes are there, therefore there will be 3 number of neurons will be present in the output layer. Okay, so this is the input layer, this is hidden layer. Okay, and this is the output layer. Now here uh, the trainable parameters. Okay, so trainable parameters, how this will be calculated? So the trainable parameters for a single you can say the neural network will be equal to the trainable parameters of the neural network equal to number of neurons in input layer multiplied by number of neurons in hidden layer plus number of neurons in hidden layer. Okay, so this is for one combination. Okay, so up to here. So suppose if we are having this calculation here. Okay, so how many number of neurons there? 1, 2, 3 and 4. Okay, so number of neurons in the input layer are 4. So 4 multiplied by number of neurons in the hidden layer. How many number of neurons are there? 2 number of neurons are there. So 2 plus 2. So in this we are having how many? 8 plus 2, 10 trainable parameters. Okay, so for this combination input layer and the hidden layer, we are having these 10 trainable parameters. And for this, similarly, we can do that the number of neurons in the hidden layer multiplied by number of neurons in the output layer plus number of neurons in the output layer. So here we are having 2 number of neurons in the hidden layer multiplied by 3 number of neurons in the output layer plus 3 number of neurons in the output layer. That will become 6 plus 3, 9. Okay, so the total trainable parameters will be 10 plus 9, 19. Okay, so for this neural network we need to find out the 19 parameters. Okay, we need to find out the 19 parameters. So as you have heard, like our pre-trained model is having 5 billion parameters, 3 million parameters, right? So GPT for the advertisement of different models, LLM models, they are doing that. We have trained our model on the billions of parameters, right? So these billions of parameters are nothing but these parameters, the values of the weights and the biases. These trainable parameters are nothing but these trainable parameters. Okay, so here the calculation is very simple. Whatever may be the values that we are having in the preceding, okay, like here we are having some number of neurons. Okay, multiplied by whatever may be the number of neurons here plus number of neurons in this layer. Okay. Similarly, number of neurons in this previous layer multiplied by number of neurons in this leading layer plus number of neurons in this leading layer. Okay. So, and after calculating the number of you can say the trainable parameters in each layer, we add all of them, then we can say that these much trainable parameters we need to calculate for this particular neural network. Yes.
So that was a clip from our AI certification and job focus program where our expert covered the fundamentals of deep learning, from perceptrons and activation functions to how modern AI models are built and trained. These are the exact skills that map directly to AI/ML engineer, data scientist, and research roles in today's job market. Also, to go deeper and accelerate your career in the field of AI/ML, GenAI, data science, and Agentic AI, make sure you register for our free masterclass given in the description. Also, if this video helped you, subscribe and drop a comment sharing what additional AI/ML topics you'd like us to cover. And also make sure that you watch this video next.